When a technician crosses the threshold of a reactor room, they are stepping into an environment saturated with invisible kinetic energy. If those high-velocity particles penetrate their suit, they will interact violently with the water and organic molecules inside the worker's body. At the cellular level, these collisions rip electrons from their orbits, causing severe biological deformation. This chart shows the escalating symptoms of human radiation exposure, measured in REMS. A mild dose might temporarily reduce white blood cell counts, but as the absorption approaches the 400 to 1,000 range, it triggers acute illness, bone marrow destruction, and early death. To protect the people working in these environments, engineers cannot rely on guesswork or trial and error. They have to build perfect, impenetrable shields on the very first try, using precise mathematical calculations. Designing that ultimate shield requires knowing exactly how radiation behaves in the specific millisecond it collides with solid matter. Down at the subatomic scale, radiation is essentially a barrage of high-energy projectiles crashing into the target atoms of whatever material stands in their way. Take a high-energy neutron. Because it carries no electrical charge, it can slam directly into a target nucleus in a process called neutron capture. The target atom absorbs the neutron, forces its way into a highly unstable, excited state, and then immediately expels a wave of gamma radiation to shed the excess energy. Charged particles, like protons or alpha particles, behave differently. They penetrate matter through inelastic collisions. As they push through a material, their electrostatic force violently strips electrons from surrounding atoms, leaving a trail of ionized matter in their wake. Then there is Bremsstrahlung, a German word meaning breaking radiation. This slide illustrates the mechanics. When a fast-moving charged particle approaches an atomic nucleus, the strong electromagnetic forces act like a brake. The particle decelerates, and the kinetic energy it loses is instantly converted into electromagnetic radiation. Physicists use the equations seen here to calculate this exact energy loss, based on the particle's charge and mass. Every single one of these collisions drains a specific amount of energy from the projectile. Measuring that exact drain rate is how we figure out how to stop the particle entirely. Zooming out to the macroscopic scale, physicists measure this drain using a standard absorber setup. This diagram shows a radiation source firing a fine collimated beam through an absorbing material, with a detector on the other side measuring exactly how much intensity makes it through. The results give us the core engineering formula for radiation shielding. I equals I sub 0 times e to the power of negative mu x. Here, I is the final intensity, I sub 0 is the initial intensity, and x is the physical thickness of the shield. The most important variable is the Greek letter mu. This is the total absorption coefficient. It represents the stopping power of the specific shielding material, determined by combining the electronic, atomic, and mass properties of its individual atoms. By plugging mu into a related equation, engineers find the half-thickness value. This tells them the precise physical threshold of lead, concrete, or water required to cut the incoming radiation intensity exactly in half. This means that shielding a room isn't an arbitrary estimation. It is a rigorous, calculated outcome derived straight from the probability of subatomic collisions. But stopping radiation is only half the equation. Safety protocols measure energy differently depending on whether it travels through the air or strikes human tissue. First, we measure the environment using the Röntgen. This unit defines the quantity of gamma or X-ray radiation strictly by the ionization in empty air. However, once that radiation strikes a solid mass, the measurement shifts to grays, or rats. 1 gray represents exactly 1 joule of physical energy actually absorbed by 1 kilogram of matter. The final and most crucial unit for human safety is the sievert, historically the rem. The sievert takes the absorbed energy and multiplies it by a specific quality factor to calculate true biological damage caused by different particle types inside human cells. These different units allow us to translate abstract energy loss into a standardized scale of human health risks. With the risks quantified, safety relies on 3 golden rules of external mitigation: minimize time near the source, maximize physical distance from it, and place calculated shielding in between. In laboratory settings, this is applied directly. Stacking dense lead bricks intentionally interrupts subatomic collisions long before they reach the human body. It is worth noting that these physical barriers only work against external exposure. Internal risks, like consuming food or water contaminated with radioactive isotopes, bypass those carefully engineered shields entirely, placing the decaying atoms directly inside the biological system. But when properly applied, these physical and mathematical protocols are highly effective. From nuclear power plants to hospital diagnostic rooms, workers safely handle radioactive fuels and medical devices every single day without suffering biological damage. The dense mathematics of particle physics provides the necessary foundation for human safety. By calculating the exact behavior of the invisible, we build the armor that allows humanity to safely harness nuclear power